Okay, cool. All right, so we are still on topic 2. So we're talking about energy and energy transfer in this unit. Last time, we talked about units for energy, the different types of energy, um, and we started talking about conservation of energy. So essentially the idea that the net change in the total energy of our system has to be equivalent to what's added in minus what comes out. So all of our energy, no matter what form it's in, has to be accounted for it in some shape or form. And then we did an example about cooling in a tank. And this is kind of where we left off. So heat transfer is one of the topics that we're going to talk about in this class. Right now, we're going to talk about it a little bit, and then we're also going to talk about it in future units in more detail. But just to kind of summarize heat transfer today from an energy standpoint, hopefully we know from experience, just living our lives on the earth, that if we take a cold can of soda and leave it on a table at room temperature, what happens to it? Does it get colder? It warms up, right? Okay, so it's going to warm up. And then kind of on the flip side of that, if we put a hot mug of coffee left out on a table, it cools down, right? All right, so this type of energy interaction is called energy transfer by heat. Where heat is defined as the form of energy that's transferred between two systems or between a system and its surroundings by virtue of a temperature difference. All right, we are going to give heat a variable, and that variable is going to be Q. And heat is always transferred from a high temperature to a low temperature. And this is going to continue until the thermal equilibrium has been reached. As a form of energy transfer, heat has energy units. All right, so heat has units of kilojoules, BTU, or feet times pounds of force. And then when we're talking about heat transfer systems, there's a few key terms that are going to be useful for us to know. The first one is an insulated system. So an insulated system, can anybody guess what that might mean? Yeah. So we have no heat transfer interactions for a system like this. So, and I'll note that this refers to an idealized thermodynamically insulated system. That's worth noting here because a purely insulated system only exists in theory, right? As much as we may want to insulate something in real life, it's not going to be perfect. Okay. So in this kind of theoretical insulated system, this means that we have no heat transfer interactions between a system and its surroundings. So in other words, mathematically, we would write this as Q is equal to 0. And we would draw this as, it's usually kind of sketched out as a fixed, like how you would sketch out a fixed surface. So if there's little hash marks all around the body, that usually indicates insulated. Okay. The next term that we need to make use of is an adiabatic process. So an adiabatic process is kind of of a variation on our insulated system, but now we're talking about a process. So this is a process that involves no heat transfer. All right, so again, we're saying that Q is equal to 0 for our process. Okay. We also are going to use the rate of heat transfer. So our rate of heat transfer is the amount of heat transferred per unit time. We give this the symbol Q dot. All right, so the dot over a variable always refers to a time rate of change. So for example, Q dot is dq dt. And then if you see a dot appear over anything else, it also implies a ddt. Since it's a time rate of change, then our units are going to be kilojoules per second, which is equal to a kilowatt. Or we can also use BTUs per second or BTUs per hour, for example. All right. If we were to want to compute the amount of heat transferred during a process between two times, and I'm going to call these two times T1 and T2, we would do the following. So we would say the total amount of heat that's transferred is the integral of Q dot integrated from T1 to T2. All right, so in this case, T is equal to time. If Q dot is a constant, what does this integral turn into? We can pull it out of the integral, right? Any constant can come right out of the integral. So we have Q dot integral of dt from T1 to T2. What does this integral look like? It's okay. Yeah, just T2 minus T1. Is it Emma or Sophia? Okay. You're Emma, right? Okay. You sit next to each other. It's hard for me. Okay. I'll get there. All right. And then this we can sometimes refer to as delta T. So this is just the time interval for the process. And one small note here, Q and Q dot are not properties. Okay. Any questions so far? Okay. Another term that's important is our heat flux. So we have the rate of heat transfer. We also want to know about heat flux. And heat flux is the rate of heat transfer per unit area. All right, so instead of per unit time, now we're talking about rate of heat transfer per unit area. All right, so Q dot, where we have, this is a lowercase q. This is just our Q dot, so this is our rate of heat transfer that we had before, and we're going to divide by area. All right, so this A is the heat transfer area. So for example, if you had, for example, a hot tub outside in the winter, this is a very lame sketch of a hot tub, but just use your imagination. And it's filled with a hot water, and you have cold air, right? Generally, heat is going to go from hot to cold, right? So we have our Q dot this way, and then this is the area over which we would calculate the heat flux. All right, so this is the exposed surface area. Does that make sense? All right, if the heat flux is known, so if we know lowercase q dot, then we can calculate capital Q dot by integrating over the area heat flux times dA. Okay. Okay. Any questions on those terminology? All right, great. Okay, so there are three basic modes of heat transfer. I'm guessing we already know them. Can anybody tell me a mode of heat transfer? So what would it be called if you have heat transferring between two solids in contact with one another? Yes, this is conduction. Fantastic. What if you have heat transfer with a fluid moving around and an object? Convection, yes. Convection. And then what about the third one? Radiation, yes, fantastic. Okay, so let's talk a little bit more about each of these in detail. So this conduction is heat transfer between two, well, it could be more than two, between stationary bodies. Due to contact. All right, so stationary bodies mean this includes all solids and fluids, so a liquid or a gas, as long as that fluid or liquid is or gas is at rest. All right, so it cannot have, velocity must be zero. All right. This is caused by the random motion of molecules or atoms. And or electrons. And it is the movement of energy from a more energetic material to a less energetic material. All right, so from hot temperatures to cooler temperatures. This can also be thought of as heat by diffusion. All right, so it just diffuses out in a uniform sort of a way. All right. Some examples of this include heat transfer between your hand and a hot pan, for example. Between an iron and clothing. Etc. Okay. Convection, on the other hand, is a variation on this. So this is heat transfer, energy transfer between a solid surface and an adjacent moving fluid. The fluid can be a liquid or a gas, of course, when they're at different temperatures. This mode of heat transfer includes effects of conduction and advection or motion. Okay, so you're always, anytime you have material in contact with it, another material, and there's a temperature difference, you'll always have conduction hanging around. If you also have movement between one of those materials, then you'll also have advection. So this is essentially heat being carried along with the flow. So heat goes along with the flow. And so if you have that situation, then convection will lump those two effects together. You don't have to consider conduction separately from convection because convection takes into account both of those. Does that make sense? If you're an ME student, we talk about convection extensively in ME 3500. Okay. There's two types of this, which I'm just going to inform you of. I'm not going to belabor it because this is a 3500 topic, but there's forced convection. So this is when the motion of that fluid is caused by an external mean. So things like fans or the wind outside. And then there's also what's called natural convection. And this is the flow being caused by buoyancy forces. So so essentially what happens is if you imagine like hot asphalt and then you have air on top of it, when air is heated, it gets less dense and so it'll tend to rise, right? So you can have flow that generates just because of the conduction element of it and then causes natural convection. So if you've ever kind of looked up a hill on a hot summer day and seen that kind of like wavy, miragey sort of look through the air, that's natural convection. Okay. I could talk about convection all day, but I won't. Third one that we have is radiation. Radiation is transfer of thermal energy of thermal energy by electromagnetic waves in a particular wavelength from a point at higher temperature to a distant point at lower temperature. All right, so this is due to changes in electron configuration of atoms or molecules and it's transported due to electromagnetic waves or phonons. Oh, transported as phonons. So these are electromagnetic waves. Okay. Radiation sort of transfers heat at its best in a vacuum. So in space, for example, which means that there's no need for the presence of matter to do this form of heat transfer, okay? Or a medium, for example. Some examples of this are heat transfer from the sun to the earth. Heat transfer from a heating lamp or a fire. Okay. So this is all I'm going to say about heat transfer for the moment, just kind of a broad overview of the different types that exist. And in this class, we're going to focus primarily on conduction. Sort of later on in the class, convection, as I mentioned, is covered extensively in 3500. And then radiation is explained in a lot more detail in intermediate heat transfer, which I don't recall the number for, but it's an ME class. Okay. Alrighty. Okay, so let's shift to work. So work is energy transfer associated with a force acting through a distance. So to write that in terms of math, work, so work is going to be denoted with a W, is equal to F, which is a vector, so our force vector, times a distance, and then we're going to integrate that over the path that we've taken. So if we have a little body traveling over this path, so this is our path S, going from S1 to S2, and it's moving because of a force acting on it. The work that's required to get that body from S1 to S2 is the integral of that force integrated over that path. All right, so work is W, and then our force is F, and then we're acting through a distance ds. Okay. All right. Work is done by a system on its surroundings. If the sole effect of everything external to the system could have been the raising of a weight. All right. So, oh, this is very blurry. I apologize. Um, so here is an example of our system. So we have energy from a battery coming into our little motor here. And that motor is then turning a paddle wheel, which has an effect on our system. Okay. If the energy crossing the boundary of a closed system is not heat, then it must be work. So if you remember when we were talking about summing up the differences in and out of energy coming in and out of our system, we know that that change in energy has to be sorted into work or heat. So if it's not work, it's got to be heat. If it's not heat, it's got to be work. Those are your two choices. Okay. Power. So a lot of our thermodynamic analysis that we do in this class are going to be concerned with the time rate of change at which energy transfer occurs. And power is the rate of energy transfer by work. We're going to denote this as W dot. So anytime we have a rate, we have that dot because that means dW dt. All right. And its unit is kilojoules per second or kilowatts. And 1 watt is equal to 1 joule per second. We can also use units of BTUs per hour or BTUs per second. It should come as no surprise that these are all the same units that I wrote down for Q dot, because in our conservation of energy equation, we sum Q dot and W dot, so they have to have the same units. Another unit that you may see is a horsepower. So 1 horsepower is equal to 550 feet times pounds of force per second. That's a handy conversion. All right. We can integrate power over the time that it takes to do a process to get the work transfer. So the work that's done is equal to the integral from T1 to T2 of W dot dt. So this is just like the integral that we set up with Q and Q dot. We're just trading out for work. All right. Most electrical appliances and components are rated based on their power usage. So we should talk about electrical work. Electrons crossing the system boundary do electrical work. If a current, which the symbol that we're going to use for current is a capital I. So if we have a current I that's driven by an electrical potential difference, which is of course the voltage with that script dV, if that crosses the boundary of a system, then the electrical power input to the system is given by W dot E. So this is, I'm just using the subscript E to denote that it's electrical work. And this is equal to, hang on, I don't like that, V times I. I'll try to make this V distinguishable from velocity V or volume V. So many V's. All right. So for example, if we have an electrolytic cell, for example, and this is our system boundary. And we have our current coming in here. So this is our current coming in this way, and then it comes out the other side. Minus. Then the difference between these two is our voltage. All right. Couple of notes on this. So note that 1 watt is equal to 1 volt times amps. The electrical work input during a length of time, delta T, is given as the following. So we have WE is equal to the integral from T1 to T2 of W dot E dt. So this is kind of a variation on the same equation that I wrote above. Works for electrical work as well. And then if W dot E is a constant, this equals W dot E T2 minus T1, or W dot E times delta T. Any questions so far? Yeah. Oh, yes. So this is volts. This is amps. Okay. Okay. So, question for you. If any of you have an electric bill, what units is your electrical consumption listed in? Does anybody know? Kilowatt hours, right? Yeah. So it comes out, it'll be printed out as a kilowatt hour. So this is 1 kilowatt times an hour, which is 1 hour, which is an energy quantity. And let's do a conversion to get this into joules. All right. So if we have 1 kilowatt hour, we want to first convert from kilowatts to watts. So 1 kilowatt is 1,000 watts, right? And then 1 watt is 1 joule per second. And then we know that 1 hour has 3,600 seconds in it, right? So our hours cancel out. The kilowatts cancel out. The watts cancel out. And the seconds cancel out. And what we're left with is 3.6 times 10 to the 6th joules. So this is 3.6 megajoules. Feels like a lot more energy put that way, doesn't it? Okay. So that is electrical work. We can also have shaft work. So a rotating shaft is commonly encountered when we're talking about machinery, like engines. And in these systems, the power is transmitted from a shaft rotating at a rate of n dot number of revolutions per unit time. And it's exerting a torque T on the surroundings. So I'm just going to draw a picture of what's going on here real quick. So Here's the shaft, and then we have a torque applied here, which is equal to the force times the radius. So we have our radius, R, and actually, sorry, let me move this. So this is our force, and our resulting torque is equal to F times R. This shaft is going to rotate at a rate of n dot. And then our shaft work, so W dot SH, I'll write it up, is equal to torque times omega, where omega is the angular velocity in radians per second. Radians isn't really a unit, so the units of this is per second. Okay. All right, so if we have n dot, which has units of revolutions per minute, we can convert to omega by the following. So we have omega is equal to 2 pi n dot over 60. And this gives us radians per second. So we can write that W dot for this shaft is equal to 2 pi n dot times torque. Let me just, so this symbol that I've handwritten here is meant to be torque. Yeah. Oh, yes. Thank you. Thanks. Any other questions before we do an example with this? Okay. Okay, we want to determine the power in kilowatts transmitted through the shaft of a car when the torque applied is 200 Newton meters. And the shaft rotates at a rate of 4,000 revolutions per minute. All right, so let's talk about what's given to us. So what do we have in this problem? We have torque. So this is 200 Newton meters. All right, and what else do we have? Yeah, we have n dot, which is 4,000 RPM. All right, and we want to find W dot shaft, right? So our equation that we're going to use is that W dot shaft is equal to torque, that's not a good T, torque times omega, or torque times 2 pi n dot over 60. All right, so I'm just doing omega is equal to this, since we are given n dot, right? Okay, so we are given torque and we're given n dot, so we have everything that we need to solve this. So let's do it. So we have W dot shaft is equal to torque, which is 200 Newton times meter, times 2 pi divided by 60, where 2 pi represents radians, right? And then 60 is seconds, right? And then we're going to multiply by n dot, which is 4,000 revolutions per minute. And actually, let me move this so there's a bit more space here. Okay, so I should have maybe done this earlier, but the 60 seconds in the denominator comes from the conversion that we have 60 seconds in a minute. All right, and then the 2 pi radians arises because we have 2 pi radians in 1 revolution. Okay. Does that make sense? Hopefully. Okay, cool. So let's do some cancellation with the units here. So we have revolutions balance one another. The minute goes away. And then we need to sort out the newtons and the meters to get to kilowatts. All right, so let's do that with the following conversion. So we know that 1 Newton meter is a joule. So we can cancel this. All right, and then we have, oops, 1 joule per second is a watt. All right, so I have joules that cancel, and then these seconds balance each other as well. So what I get is 83,800 watts, or 83.8 kilowatts. Does that make sense? Are there questions? Good. Okay. Couple key points before we move on from this. A quantity that's transferred to or from a closed system during a process is not a property. Since the amount of such a quantity depends on more than the initial, sorry about this, more than the initial and final state of the system. Both heat and work must cross the boundaries of the system. Systems possess energy, but not heat or work. It's kind of a different way to state the previous statement on number 2. Both heat and work are path functions, which means the amount of heat and work that happens as a part of a process depends on the path that you take. Okay? An infinitesimal or a differential amount of work or heat or work is designated with the letter lowercase delta, or in other words, delta W or delta Q. And note note the difference between dQ or dW. All right. And then the key equations that we talked about is that the work done between a process that goes from state 1 to state 2 is equal to the integral from state 1 to state 2 of delta W. And we also have that Q12 is equal to the integral from state 1 to state 2 of delta Q. So this is important. Since this delta is not the same as dW, that means that if we have the integral from 1 to 2 of delta W, this is not equal to 1 W2 minus W1, okay? Okay. Is everybody feeling refreshed? Because I have some important lab announcements based on questions I just got. Is everybody ready to talk about Lab 0 for like a hot minute? Okay. I'm just going to add a page in here quickly. So if you're looking back on the notes and you're like, what in the world is this? You know now. So this is a Lab 0 aside. Okay, so in Lab 0, you are kind of doing this fictitious, imagine that you're trying to calculate density of a golf ball or several golf balls, right? And so you're provided data for 10 different golf balls. You're given mass and you're given the diameter, right? I would like you to imagine that each of these entries is a nominal value. So assume that you have taken the same golf ball and measured its diameter and its mass 10 times, okay? So you have 10 unique golf balls, and the data that I'm giving you, that's your average of all the repeated measurements that you've done. So let me write that down one more time. So let's say that this is 1.76 ounces, and then this is, I can't remember what the values I gave you were, 2.5 centimeters. This is maybe wrong, but just imagine, okay? So assume each row represents the mean of taking these measurements ten times. Okay, so you have 10 golf balls, and each row is a different specimen. I might have spelled that wrong. Does that make sense? Okay, so you've taken repeated measurements of 10 different golf balls that you're measuring. All right, so each of the values in that table you can take as a nominal measurement. And then in the report, I want to see two plots. So I want to see density as a function of mass, and I want to see density as a function of diameter, right? We know that density is equal to mass over volume, and we know that volume is 4/3 pi r cubed, which is d over 2 cubed, right? So this is the equation that you're going to need to sort out the uncertainty for, right? So use this to find U row, right? Because you are given UM and UD in some form, right? The other thing that I want to mention is on this plot, you should have 10 symbols for your 10 golf balls that have been measured, right? And you want to put on error bars, right? So you might be confused as to which quantity of uncertainty to put for the error bars. So these error bars must have the same units as your axes. All right, so on the horizontal axis, we have, let's say, kilograms for this example. So you're going to want to use delta M because that has units of kilograms, right? So don't use the U sub M for this. You're going to want to use the version with the units. So for example, if you have U sub M, you're going to want to use, if you have U sub M, delta M is just equal to UM times M, which is, this is the nominal value. Does that make sense? I'll keep these in the notes so you don't have to take a picture. Or you can take a picture if you want. It's fine. Does this make sense? Are there other questions, clarifying questions about Lab 0? No? Okay. And then just to reiterate from the beginning of the class, the video that I'm posting about MATLAB will walk you step by step through all the plots you have to make for this lab report and then a little bit beyond, because we're not doing curve fitting and stuff yet, but I included how to do that. Okay, yeah.
This looked like as it goes farther on the mass axis, the error bars would get wider.
So it kind of depends. I can't remember how the uncertainty was given for mass. I think I said it was just the readout is to 2 decimal places or something. Is that right? So readout for mass looks like this, right? I don't know if it was kilograms, but just imagine, right? Okay, so if this were the case, then we know that our delta M is going to be equal to half of the smallest measurement this scale can do. The smallest measurement that it can do is 0.01, right? So we'd have 0.01 kilograms divided by 2. So your delta M is going to be this. All right, and that doesn't matter what the measurement was, that's the delta M. Okay, this will change, the U sub M changes because if you're dividing by M, the percentage changes, right? Other questions? I don't mind if there's more. Okay. And I'll put this in an announcement on Moodle too, just in case, but feel free to email me if there are more questions. Okay, cool. All right. Let's talk about sign convention for heat and work. Okay, so if you remember, our conservation of energy equation looks like the following. So we have energy at state 2 minus energy at state 1 is equal to energy in minus energy out, right? All right, so we need to use a sign convention, and this is what we're going to consistently use throughout this entire course. And that is that heat transfer, which is Q, is considered positive if it is input to the system. And then it is negative if it is lost by the system. All right, the same thing applies to Q dot. All right, so if I write this down formally, if Q is greater than or equal to 0, this is actually just greater than. Heat is input. If Q is less than 0, heat is output. And then Q net, or just Q, is equal to the sum of the Q ins minus the sum of the Q outs. All right, so in this formulation, if I draw a system, so this is our system. All right, and we have Q out and two Q ins. If this is our picture, then we will use the positive value of each of these in this expression here. All right, so essentially what I'm saying is that this minus sign right here takes into account that we're treating a Q that is leaving the system as negative, right? All right, so what this does not mean is that we have Q in plus Q in. I should have labeled these 1 and 2. So a QN1 and QN2. So for this system that I've drawn, this bottom equation doesn't mean QN plus QN1 plus QN2 minus Q out, right? It's just minus Q out. Does that make sense? Okay. 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 Work is considered positive if it is output by the system. And it is negative if input to the system. Okay, so the convention is that if W is greater than 0, this is work output. If work is less than 0, this is work input. All right, so note that this is opposite. From Q. Okay, so we have then that the net work is equal to W, which is equal to the sum of the work out minus the sum of the work in. So this is our net work output. Okay. So if I draw my little system again, and then I draw my control surface around it. If we have work coming in and then work out here, and then another work out here called 1 and 2, we're going to do the same thing. So like we will take the quantities W in, W out 1, and W out 2 and treat them all as positive quantities when we use this bottom expression here. So we have W net for this case is W in sorry, we have W out 1 plus W out 2 minus W in. Okay. Does that make sense? Okay, cool. When we're solving a problem, we can either assume the direction of heat or work and then solve for it. And this, wow, the sign to the answer will indicate whether the direction of energy or work that we assumed was correct or not. All right. So, given this, we can require the conservation of energy for a process going from state 1 to state 2 involving a closed system as the following. So we can say E2 minus E1 is equal to E in minus E out, or E2 minus E1 is equal to Q in plus W in minus Q out plus W out. Okay, I'm going to do a little bit of rearranging here. So we have E2 minus E1 is equal to Q in minus Q out plus W in minus W out. And then if you remember from our discussion about work, net work is work out minus work in, right? So I'm just going to switch the order and bring the minus sign outside of that second term. So I have Q in minus Q out minus W out minus W in. All right, and so what we have here is our Q in minus Q out. That is our net Q. And then minus W out minus W in, which is our net work. All right, so we end up with E2 minus E1 is equal to Q minus W. Okay, so a note here. So Q in, Q out, W out, and W in are all positive values. But Q and W can be positive or negative. Okay, so if you end up with a negative sign, it just means that you have made the wrong assumption when you made your drawing. So you called something that was a Q in that should have been a Q out, for example. Okay. Okay, let's do a little bit of a discussion about expansion or compression work, otherwise called moving boundary work. So if we consider a quasi-equilibrium expansion or compression process of a fluid in a piston cylinder, and just to reiterate, when I say quasi-equilibrium, that means that obviously the piston is moving inside of the cylinder here, but we're assuming that it's happening slowly enough that each of the little states that we move through are at equilibrium themselves. All right. So like we move a little bit and it gets equilibrium, and we move a little bit and it gets equilibrium. Okay. Okay, so we want to evaluate the differential work done by or on the fluid for an infinitesimal displacement dx of the piston. And I am going to draw a picture here. So here is our cylinder. And we have a piston in here. like this. And so this is, let's see, this is the location of our piston at time 1. And then at some later time, it's going to move to this location. Oh, that's bad. Okay, so here is new location at some later time T2. Okay. So we have a few things that we can note on here. This surface area is A. That stays the same. And our system at T=1 is this amount of fluid in the cylinder here. All right, so this is a gas or a liquid in here. And we have acting on our piston a force which is equal to pressure times the area. All right, which is causing us to move to our second location in blue, right? So when we move, our system expands, right? So when that cylinder moves to the right, our system expands. So our system at T2 is now all of this fluid. Okay. And we said that the piston has moved an infinitesimal displacement dx, which means this is the distance dx that we're talking about. Okay. And what else do we need? This is my x coordinate system. And I think that's all we need. So one other note, expansion, for an expansion process, that means that our velocity is going, or our velocity, our volume is increasing. And for compression, it's decreasing, right? Does the setup make sense? Cool. Okay, so we want to find the work associated with this force, P times A, over this displacement dx, where P is our absolute pressure of the fluid, and then A is the cross-sectional area of the piston, which hopefully that picture conveys. Okay, so let's talk about our infinitesimal work. So if you remember, that symbol for infinitesimal is lowercase delta. And we have work. B, so this is our boundary work, is equal to force over the distance dx. All right. We can rewrite our force. I'll do a different color. Our force, we can write as P times A, right? So pressure times area times dx. And then there's something convenient that arises here. So if we have A times dx, that is actually our differential volume. right? That is this volume here. Area of the base times the height, right? Okay, so this dV is the change in volume for this infinitesimal process. Okay, so for a process that goes from 1 to 2, we have pressure at 1 and volume at 1 going to a pressure at state 2 and a volume at state 2, right? Okay, so we know that WB is the integral from 1 to 2 of the differential or the infinitesimal work B, or we can substitute the integral from 1 to 2 of P dV, which means that we want to integrate from volume 1 to volume 2 of P dV. Is everybody okay with the substitutions that I made through there? Okay. So essentially what we're saying is that the absolute value of the boundary work is equal to the area under the PV curve. Okay, so if you remember in the last unit, we talked about process paths, and I said we were going to chart out a process by comparing two states. And so the two variables of our states in this case are pressure and volume. Okay. So we, in this particular case, we're looking at an expansion, right? So we're starting at a location 1 where our pressure is high and our volume is low. And then we are going to expand our chamber to a position where our volume is higher and our pressure is lower. Okay. So our second state is right here. Okay. So our process path. No, there we go. Goes like this. So we're moving from 1 to 2. And the area under here is our work. Does that make sense for everybody? Okay. When we're looking at our little differential circumstance, essentially what we're doing is we're zooming in on this curve where this distance is our dV. All right. So we're looking at a little tiny piece of this general process. Okay. So for an expansion process, we have that the change in the volume is going to be greater than 0, right? We're expanding our volume. So that means that WB is also going to be greater than 0. Or in other words, this means that we have work output from the system. And then for a compression process, we have the opposite. So we have that our change in volume is negative. Our volume's going down, we're compressing, which means that WB is also less than 0. So this means that work is input. All right, so hopefully that's intuitive. If you want to compress something, you need to apply work to that system to do that. And then if it's expanding, your work is output or put on the system around it. Okay. Are there any questions on this? Okay. Okay. Now we're going to talk about a specific type of process that we've mentioned before, a constant pressure process. Does anybody remember what name that has? It's related to a barometer. Isobaric process. All right, and we want to determine the boundary work during a process 1-2 if it's a constant pressure process. All right. So if P is constant during the process, constant during the process, what that means is that P1 is equal to P2, right? Pressure is not changing. P1 is P2. And so if you remember, we have WB is equal to the integral from 1 to 2 of P dV. So since this is a constant, we can take it out of the integral. So we end up with P integral from V1 to V2 of dV. Or in other words, P times V2 minus V1. Alrighty? Okay, remember that specific volume, so this is specific volume, is equal to V over M. Or in other words, we can write our volume as the specific volume times mass. And M here is the mass of our system. If we have a closed system, what does that mean about M? It's not changing, right? Closed systems contain the mass in the system. Mass does not leave, so that means that M is a constant. Thank you. All right, so that means that V2 is equal to M times specific volume at 2, and then volume at 1 is equal to mass times specific volume at 1. All right, so that means that if P is a constant, so if we have an isobaric process, that means we can write our work as the mass times the pressure times the change of specific volume of the system. Okay, if we look at this type of a process on a PV curve or diagram, so we have P and V. We have P1 is equal to P2, right? But our volume is changing. So the area under our process curve is going to look like this. Okay. Any questions so far? All right, cool. Okay, so an example of a constant pressure process is the quasi-equilibrium heating or cooling of a fluid in a frictionless free piston cylinder device. So this is essentially a piston that's supported by the fluid only. So it will look like this. So we essentially have, this is our cylinder. And then we have our piston in here. And you'll notice I haven't drawn anything connected to it. It is solely being supported by the fluid inside of the cylinder, okay? So we have our fluid in here at a pressure P. And there's a fluid in here. Okay, so this is our free piston. Just to make sure that it's notable the difference between this system and a not free piston, for example. A free piston is not a drawing that looks like this, where we have, for example, a spring attached to this thing or a shaft attached to it or any other thing attached to it, or stops at the bottom preventing it from going any lower than that spot. None of these are free pistons. Okay? Not free pistons. All right, so you cannot take a picture like this on the right and assume a constant pressure process. Okay? All right. So going back to our free piston, in this circumstance, we know that the sum of the forces in the z direction are going to be equal to 0. All right, so we basically have the mass of the piston itself, so the gravitational force due to its mass, is balanced with the pressure of the fluid pointing up and the pressure of atmosphere at the top, right? So we have pressure of atmosphere on the top. And let me just draw a free body diagram real quick to make this abundantly clear. So we have atmospheric pressure on the top. We have the fluid pressure on the bottom, which I'll try to make this look bigger. All right, and then we also have mass times gravity, right? So these are our forces that we have. It's in a quasi-equilibrium, so there's no net force on this piston. Otherwise, it would be accelerating one way or the other. All right, so our sum of our forces is equal to 0, and it is the pressure times the area of the cylinder, or I'm sorry, of the piston pointing up, minus atmospheric pressure times the area that points down. And then we have mass times gravity. Okay, so this means that P is equal to the atmospheric pressure plus mg divided by A. Okay, any questions on like the distinction of a free piston versus a not free piston or any of that? Okay, cool. We can also have a constant volume process. All right, so these are processes that will involve a rigid container. That's the best way to keep our volume constant. All right, so if we have a rigid tank that contains air, so this is a rigid tank, initially at 500 kPa and 150 degrees C, and then as a result of heat transfer to the surroundings, the temperature and the pressure inside the tank dropped to 65 degrees C and 400 kPa, respectively. And we want to determine the boundary work done during this process. So let's draw a picture first. So here's our air tank. And then we're going to draw our control system here, right along the boundary of the tank. And it's air in here. And we're already told that heat is being transferred to the surroundings. So we know that we have a Q out, like so. And so our system is this air tank. And we have two states given to us. We have state 1 and state 2. So our initial state, state 1, is that our pressure P1 is 500 kPa and T1 is 150 degrees C. And then state 2 is P2 of 400 kPa and T2 is 65 degrees C. We want to find WB, right? Okay, so we know that WB is the integral from state 1 to state 2 of P dV, which can also be written as the integral from volume 1 to volume 2, pressure dV. All right, but this is a rigid tank, right? What does that mean about dV? Do we have any change to the volume of the tank? No. So this is 0. So what does that mean about our boundary work? It is not a trick. It's just 0, right? So we're multiplying this whole thing by 0, so we have 0. Does that make sense? Okay. This is a good stopping place. This next example is a little bit longer, so we'll start that on Thursday. Okay?